Welcome to Data Skeptic Animal Intelligence. Optimization problems involve the use of numeric methods to find an ideal solution in an otherwise unwieldy search space. You can find optimization problems in every single industry. Today we explore a framework around voyage optimization for planning ship transport in a way that not only reduces fuel costs, but also reduces the impact that ship noise has on marine life.
I'm Akash Venkateshwaran. I'm a graduate student at University of British Columbia, Vancouver. My research mainly focuses on developing technologies to mitigate anthropogenic noise, specifically in marine activities. Our goal as a research lab is to create this innovative solutions in order to ensure eco-friendly and efficient maritime operation while protecting the marine life specifically from noise pollution. I work on a smart decision system for ship navigation in order to provide sustainable and quiet operation conditions.
Could you expand a bit on the problem of anthropogenic noise? Why is it a problem?
Marine transportation is one of the main media of transportation that we use. These ships produce a lot of noise, and we can talk about the noise source and where it actually comes from. But the problem is that the ship produces a lot of noise which can impact the marine ecosystem, specifically like killer whales, like humpback whales. The thing is, they use echolocation to kind of localize where they are in the environment. They also use the sound to get their food and also migrate from one place to another. So they rely a lot on sound and echolocation. Because of this anthropogenic noise, it kind of interferes with their daily life activities, which causes a huge problem. Especially, we can see a decline in their population ever since the increase of the number of ships in the ocean. And because of this increase, we also see there is an increase in the ambient noise level of the ocean. Our problem is trying to mitigate this and trying to reduce the overall impact of noise from ships.
So it's intuitive that the noisiness could bother a marine mammal, especially one that uses echolocation. But is there something more precise we can say about that? How do we measure the degree to which they're bothered?
I actually work with some of the marine biologists in UBC, and the way they define it is that there is also an impact on the psychological behavior of the mammals. So we have tags on the mammals which measures their movement, and also it can also capture some of the audio and the video footage of the mammal. So the way they define psychological impact is interfere their daily patterns of finding food and traveling from one place to another. We also see that they also get a lot agitated because of the noise from the ship as they get very close to the ship. So it is not quantifiable. It's not there's still a lot of research to be done. But I feel in terms of numerical quantification of the impact, we can look at, let's say, the audiogram of a specific mammal. So an audiogram is like a threshold across the frequency at which the mammals are sensitive to the noise. We can kind of compare how much the noise is exceeding that audiogram, above which it can kind of interfere with their hearing sense and also communication. So that is one way of quantifying things, but I think there is more work to be done in terms of how we can define the impact psychologically and in daily activities like a physical impact.
And to know that they're in decline in population is troubling. Maybe a little fuzzier, like it could be caused by global warming and the noise or some combination, but certainly not a good trend. How do you use technology to solve this problem?
Before I explain the technology that can reduce the noise, let me actually explain how the noise is generated from the ship. The main sources of ship noise is the propeller itself. The propeller causes something called cavitation, which is where when the pressure is below a particular point, there are these cavities formed and which can burst and produce a lot of noise. So the propeller causes cavitation phenomena, which causes the noise. There are also other sources of noise, which is like the machinery on the ship and also the movement of the hull of the ship, also causes some of the vibration and produces noise. So there are mitigation strategy that deals with the design aspect of these things, like design of like the propeller in order to reduce the cavitation phenomena. And also there is something called singing of the propeller, which is when there is a flow around the propeller, there are eddies which are formed behind the propeller, and these eddies are kind of asymmetric, which causes the force imbalance in the propeller. So if you think about it, you can think like if you have a straight rod and there is a flow around the rod, because of the eddies, it would create uneven force on both sides, which can cause it to vibrate. And that is something called propeller singing. You can kind of induce some of the vortices along the propeller to reduce that imbalancedness. So that is one way. As I mentioned, the movement of the ship also causes a lot of noise. So there is ship hull form design optimization. But the thing that I am dealing with is we already have a lot of ships and propellers which are already designed. So how can we solve that problem with the existing ships? The main source of noise is the cavitation phenomena. The cavitation has a very close relationship with the speed at which we are operating. So the higher the RPM of the propeller causes more cavitation. So there is like this complicated relationship between the speed, which causes cavitation, which causes the noise. My research is like how can we optimize the operation condition of the propeller, the existing design of the propeller with the existing ship. How can we optimize its operating condition so that we can reduce cavitation, which in turns reduce the noise? So that is the approach to the problem, optimization on ship operation conditions. I can go into more details how we model the ship noise and the propagation and do the optimization.
I want to definitely unpack all that, but I've got a, I guess, question at the front end for you. If I was a ship owner, I would assume my goal was strictly to get to the next port as fast as possible, so full speed ahead. Is that generally the strategy, or do I have a motivation to operate differently?
As a ship owner or like commercial ship designer, you want to reduce the operation cost because you want to reach the destination as soon as possible. We don't want to consume a lot of fuel. So there is this trade-off that we talk about where reducing the speed of the ship can have this negative impact on the fuel side, which can increase the carbon footprint of the vessel. More consumption of fuel leads to more cost. So that is where we try to bring this framework of multi-objective optimization, where we try to balance between the cost, which is more caused by the fuel consumption, and also trying to balance the noise impact of the ship. That is this whole framework where we define both the fuel consumption and the noise impact. We quantify that as an objective function, and we try to minimize these two with some constraints. So there could be constraints like reaching the destination within a specific interval of time. There could be other constraints like the velocity limits of the ship. There could be physical constraints of the ship. It's an optimization problem. It's a multi-objective constraint optimization problem that we are working on.
Thanks to our sponsor, the Georgia Tech Scheller College of Business. Check them out at techgradcertificates.com, especially if you're ready to become a data-savvy leader. Did you know the Georgia Tech Scheller College of Business is ranked a top 10 business school in the U.S. for business analytics? They offer a 100% online business analytics graduate certificate program. There's 4 courses covered: business analytics for managers, machine learning for business data preparation and visualization, and analysis of unstructured data. This graduate certificate is designed for professionals in any industry that want to become data-savvy leaders or just pivot into analytics. You can maintain a work-life balance and other commitments while going through this flexible graduate certificate program at your own pace. And that certificate can be your gateway to a Georgia Tech MBA. So if you want to stay ahead of the game and learn key strategies to extract information from the vast amounts of data generated every day in business, consider pursuing this certificate. Applications are open for the fall of 2024. Get started at techgradcertificates.com. So you've got cost, which I assume you want to minimize, and noise impact you also want to minimize. Are there any other optimization goals in that multi-objective optimization?
As of now, we are dealing with these two objective functions, but we can always extend this framework for other problems, one of them being greenhouse gas emission. So there are models out there that can give us an estimate of the greenhouse footprint of the ship. There is also fuel consumption. We should also talk about the weather condition of the ship. The fuel consumption is calculated based on the water resistance experienced by the ship. So the more the resistance, the more fuel we need to propel the ship forward. So we also need a weather data model to kind of predict what the resistance would be. And we want to like kind of get a rough estimate so that we can optimize the speed of the ship in order to reduce the fuel. And there is also the noise side where we use noise source model, noise propagation model, and there is also like models for the mammals, which can kind of give us an estimate of where the mammals are in the environment. Yeah, we create this whole environment where everything interacts, and we are trying to create this adaptive smart ship that can reduce its carbon footprint, noise footprint, and also not consume a lot of fuel from reaching from one destination to another.
Well, when I think of optimization problems, the best textbook one is data that looks like a parabola, right? And you find the minimum point of the parabola, and that's sort of inarguably your best solution. It seems like you may not have a parabola here, that the noise impact could go to zero. So that's the most minimal value. But then, of course, you're not delivering your goods. How do you get around that issue?
The problem that we deal with has both noise and the fuel. So if you think about it, you can think of these two objective space as like a 2D plane, and we have multiple like mountains and peaks, and we are trying to find the global minima of these two. When we do multi-objective optimization, we most probably dealing with these complex problems, we try to use evolutionary algorithms. The one I use is NSGA. It's a genetic algorithm for multi-objective optimization problems. So the idea is that evolutionary idea that we define the design variables as chromosomes, and we kind of randomly scatter them in our objective space, and these chromosomes are kind of evaluated based on the objective function, and the best one moves from one evolution to the next evolution. We try to optimize the design parameters as we move from one generation to the next generation. So eventually we try to find a Pareto friend. A Pareto friend is basically a set of solution that minimizes both objective 1 and objective 2. So there could be solutions which provides more emphasis on objective 1 compared to objective 2. So let's say you want to reduce fuel more than the noise impact, you can get solutions specifically for your needs, and there could be also solution which emphasizes more on the other objective. So we get the series of solution, and it's up to you to decide what kind of solution that you need. So we provide weights for these two objective, and we pick the trade-off solution from the Pareto friend. So yeah, there is always this trade-off where you cannot minimize these two completely. There is always some sacrifice to be made in order to solve the problem. So
Well, I know in many optimization problems, there could be several valleys where there are good solutions. I'm thinking of like if I were to try and optimize a restaurant, there are some that are very cheap food, lots of customers in a short period of time, quick delivery, and that's a reasonable solution for fast food. But then there's also a restaurant that has a smaller volume but more expensive meals, and because of that, they don't have to serve as many people. Both good solutions to the problem of how do we optimize a restaurant, but very different restaurants. Do you find that there are different pockets of solutions to explore?
yeah, definitely. It depends on what kind of emphasis that you want to give. So once we solve this multi-objective optimization problem, we get a series of solution, and we kind of post-process it to normalize everything. And we try to, again, as I mentioned, assign weights depending on what we need. There is also something called a method called TOPSIS, which is an efficient MCDM method, and MCDM stands for a multi-criteria decision-making method, which gives us an algorithm to pick the trade-off between multiple objectives. So how can we find the optimal like trade-off that can minimize both these objectives? This is based on the idea that when we normalize our objective space, the Euclidean distance from the origin, so the origin is like 0, comma 0, which is where both the objectives are 0. And we want to find the solution which is as close to the origin as possible. So once we get the Pareto friend, we compute the Euclidean distance from the origin and we kind of rank the solution based on this criteria. And we pick the one with the highest rank, which is the one closest to the origin that gives us the trade-off solution. There are also different techniques. So let's say you already have an estimate of what the solution you want. Like you already know that you want the fuel to be minimized to this range and noise to be minimized to this particular range. You can give reference point in your objective space and you can try to find the solution around that reference point. That is another technique where you already have some prior knowledge on the problem and solution that you want to achieve, and you can kind of direct the NSGA to converge towards that in the objective space.
Do you consider the environment in your approach?
So, as I mentioned before, we try to create this whole environment where we have the ship and the mammal, and we try to calculate what the noise impact is as well as the fuel consumption. As of now, in the paper, it's the optimization of the speed of the ship, but we are trying to extend the framework where it's a 3D environment. We optimize both the trajectory of the ship as well as its operation condition, which is the speed. But as of now, in the paper, we try to optimize speed along the fixed path of the ship. So the problem has two objective functions. One is the noise impact, and the other one is the fuel consumption. For the noise impact, the noise is produced by the propeller, so there is the noise source model specifically for the ship, and there, as the noise is generated, it propagates in the ocean environment. So we also have the noise propagation model, which can give us a good estimate of what the noise is received by the mammal out there in the environment. And we also need another model that can give us the distribution of the mammal in our environment. So we have a kernel density function. We specifically work on southern resident killer whales because these are endangered species that are heavily impacted by noise. So we have sighting data of these whales in British Columbia coastal region. So we have sightings of like scatter points of these whales throughout the season. So it depends on the season as well when they are migrating towards this side of the Vancouver Island region. So we have these sighting scatter points and we create kernel density function, which is just a probability distribution in the lat-long plane, which give us an estimate. Okay, let's scatter some mammals, and it gives us a probability of finding the mammal at that location. So we use that model to estimate probably where the mammals are, and we try to use the propagation model to calculate what the noise received by these mammals are at those locations, and we try to control our speed so that the noise generated is reduced, so that it propagates and it causes less impact on the mammals. And on the fuel side, as I mentioned before, like in the paper, we use a very simple model called lab killer model. It is an empirical model that is used to get an estimate of the water resistance based on the ship dimension on the propeller speed. But we also have very complicated models that uses weather data, also uses the current direction and the current speed to calculate what the water resistance experienced by the ship is, and in turn calculate the fuel consumption. So there is the fuel consumption model, there is also the noise model, and the mammal distribution model. We calculate the objective function, which is the noise impact and the fuel impact, and we try to reduce these two with some voyage constraints.
So let's say there was a very forward looking shipping company that said, we want to adopt your approach. We're going to do a pilot. They give you all the data you need about their voyage and other information, and they say, come back with a solution. What do you deliver to them? What does the solution look like?
The framework that we are creating is a decision support system. It gives the captain or the person operating the ship what the operation conditions are at different locations along the voyage. We discretize the voyage into multiple sailing legs, and we try to optimize the RPM of the propeller. But there could also be other design variables like the orientation of the ship along the path, and also like the path itself can be optimized. Just like the traffic rules we have, it has its own traffic lanes and other constraints in terms of traveling from one location to another. So we also consider that. So we try to apply these constraints in our environment where we sample within the traffic lanes. Towards the end, we provide them with the propeller RPM as of now in order to reach the destination, as well as give them that at these RPMs, like we have a good estimate that we are not impacting the mammals that much as we are moving from one place to another. As we are talking about this, there's also a program which is called ECHO program, that is Enhancing Cetacean Habitat and Observation Program. It's a program in British Columbia where they have some regulations on the ship speed in some specific location in the Vancouver Island region. It's a voluntary program where the ship can reduce its speed below a particular threshold as they are moving in those like endangered like habitat region. There are these programs which exist out there that has more like a strict rule that within this region you need to maintain the speed below a threshold. But the solution that we are trying to bring is more adaptive, where we actually model the noise and we have some kind of probabilistic inference on where the mammal is. And that way, we are bringing a more smart and adaptive regulation where people can follow that and try to reduce its environmental impact on these marine mammals.
What are some of the mathematical challenges in the optimization process? Why isn't this a trivial problem?
So there were some mathematical challenges, not just in the optimization problem, but also in the modeling side. We use very simplified noise source model and propagation model. But in reality, when we implement this framework in actual ships, we want something which is very robust and fast, and if quite accurate, we need a real time modeling of the noise from the ship. So that is where we try to bring in machine learning and data driven modeling of noise propagation. There is another paper that where we talk about machine learning models for underwater noise propagation. In the paper, we use convolutional autoencoder in order to get a transmission loss from the ship. So it gives us what the propagation loss is from the source all the way to the receiver. And based on this propagation loss, we can calculate what the noise is received by the mammals. So we also deal with mathematical problems where we're trying to model propagation of the noise itself in a fast and efficient way. We also have AIS data that gives us an estimate of where the ships are in the environment, which gives us where the source location is, and we can try to numerically simulate that and use the also the measured data to predict the noise more accurately. And there are also other environmental factors like the sound propagation is impacted by the bathymetry of the ocean, right? Because of the reflection, it is also impacted by the sound speed profile, which is the speed of the sound as you go deeper in the water. So that sound speed profile is in turn impacted by the temperature of the water, the salinity of the water, and other things. So yeah, the modeling of the noise itself is a very complicated problem that we are working on. There is also like the optimization problem. Optimization is actually relatively simple when you think about it compared to the modeling side. So there are basic rules that you need to follow when you're trying to optimize a problem, normalizing the objective space. So in the optimization problem, we also have something called hyperparameter tuning. Hyperparameters are the parameters of the algorithm that we change to solve a particular problem. So in NSGA, we have different hyperparameters, which are the mutation coefficient or the crossover coefficients. So these hyperparameters heavily influence how the algorithm converge to a solution and how it finds the global minima. It is also dependent heavily on what problem we are dealing with. We use SLAM, which is a Bayesian model based hyperparameter tuning Python software that we use to estimate what these hyperparameters of NSGA are in order to minimize the problem. Also, another thing was just exploring different methods. So, there are other revolutionary algorithms like PSO and like simulated annealing method and things like that. So you can also use gradient based optimization algorithms.
So there's, as I'm sure you know, dozens of different ways you can approach an optimization problem. And of course, we know from the no free lunch theorem that there isn't one algorithm to rule them all. What made evolutionary algorithms an interesting one to look at for your case?
We pick genetic algorithm because of the fact that we are our objective functions are very complicated, and it is also very sensitive to the input design variables. So we wanted something which is quite fast, which can deal with an objective space that has very sharp edges where you cannot compute the gradients, right? So you want an evolutionary algorithm that can compute what the local minima is without computing the gradient of your objective space. We didn't actually explore gradient based algorithm, to be honest. We had this gut feeling that evolutionary would work well for this problem. So we just went ahead with NSGA and PSO. And NSGA seemed to converge a lot faster than PSO. And we did some hyperparameter tuning to make sure that it works. And we went ahead with this particular algorithm.
Well, you'd mentioned that the modeling is maybe more complicated than the optimization. And I believe you from looking at figure 2, where I see all the components and pieces to it. Could you give just an overview, I guess, of what's involved and how you implement all of it?
This whole framework is optimization of the speed along a fixed route of the ship. So, given the route, we discretize it into multiple sailing legs. Within each sailing leg, we are trying to optimize what the speed of the ship is. Once you discretize the sailing leg, we create something called environmental configuration. As I mentioned, we need to model both the noise and the fuel. And in order to model the noise, we need to get what the environmental variables are. So these are like bathymetry data. We use JEPCO dataset that provides us an open source bathymetry along lat-long location. It's a gridded data and we can find along a particular path. So we try to interpolate along the path and get the bathymetry of the ocean. We also get the altimetry from a different source. So once we have what the environmental variables are, we extract that as a part of the environmental configuration. Again, we need to get an estimate of where the mammal is. So we use kernel density function to get the distribution of the mammal depending upon where the route is. So as of now, we are dealing with only Vancouver Island region. So we have the sighting data of southern resident killer bears, which we use in order to create our kernel density model. But depending upon the route, you create the distribution model of the mammal that you want to study on, and you create this distribution model. In this particular paper, we also have different groups of mammals. So there are actually 5 groups of mammals. One of the study provides us the audiogram of these mammals that we compare our received noise level to. The mammals are grouped into 5 groups, and we have 5 parameterized audiogram where we kind of compare the threshold with respect to audiogram and we try to minimize that. So that is like the environmental configuration. There is also like the ship configuration for the fuel. Actually, not just for the fuel, but also for the noise. We also have something called the noise source model, which is dependent on the ship characteristics, like the displacement of the ship and the length and the width of the hull and things like that. So we use something called Ross model, which is a very simple empirical model that depends on like simple dimensions of the ship and the speed of the ship that gives us the sound pressure level at the source. And we use something called lab color method, which is again a very simple empirical method that is dependent upon the ship dimension that gives us what the fuel rate is. And we calculate the fuel rate for each sailing leg, and we also calculate the estimated time. So based on the time and the rate, you can calculate the total fuel consumption. So you get the total fuel consumption along the voyage. You can also get the total underwater radiated noise intensity along the voyage. These two are the objective function, and we try to minimize these two objective function with the constraint of time of arrival and other constraints like the velocity limit, the power limit, and so on.
So, as the famous quote goes, all models are wrong, but some are useful. Is yours close enough to reality to be useful for real world voyage optimization?
Well, to be honest with you, this is a preliminary idea that we want to work on. So, as of now, again, this is a 2D framework that we are trying to extend it into a 3D environment where we have the ship lanes, and we are trying to optimize the orientation of the ship and the speed as well. So, I think once we achieve the 3D framework, we would like to test it with some real measurements. So we already have some sea trials where we use coastal guard ship to get the sound pressure level received along a fixed route. So we are going to validate what our received noise levels are. And then regarding the mammal side, that is kind of like, you cannot
Can't survey them, yeah.
we just use the survey to get the distribution, so
Sure.
you cannot do more than that. But we would try to make sure that the noise propagation model is as accurate as possible, because we have hydrophones that can actually measure the noise. And once we have that, we'll be much closer to implementing this framework in real life and trying to replace the conventional like slowdown regulations and trying to bring this adaptive framework to reduce the noise impact.
So there's certainly an option for governments to have conservation efforts and to use methods like yours as guidance for what the restriction should be. And I think that's an interesting opportunity. Is there also potentially an economic argument here? Could you convince the shipping company that it's in their best greedy interests to abide by these policies a little better?
Regarding the economic side, actually in Echo program, they pay you some incentive to reduce the velocity based on the regulation. It's a voluntary program, but they also pay you because you have lesser noise footprint from your ship. So the government can bring up some kind of like reward system where they can pay the owner to follow these regulation. So this is again a decision support system. So it gives you that you need to be operating within this range, but it is again up to the owners to follow that regulation. Yeah, I hope like we are trying to present this idea at conferences and also workshops. So we are trying to bring awareness to this problem of anthropogenic noise from the ship. So this is a big problem, and we are trying to bring more people in and also like collaborate with companies in order to make this as real as possible and bring this application to the real life.
Are there data sets that aren't available that would be helpful to your research? I mean, I can't imagine there's a good database you can look up and get everything you want to know about sound in the ocean. Maybe weather. Weather's pretty good, but what would you like to have if you could get any data?
Regarding the data, I would say I need more data on the mammal distribution model side. So we have the sighting data of southern resident killer whales, but also like these data are also inaccurate in the sense that they just provide the surface level detection, but we also need the distribution along the depth, because the noise received by the mammals is dependent upon the depth as well, so where the mammals are. So it would be a good estimate to get some data of different groups of mammals in the 3D environment, so not just the lathlon but also with respect to depth, so that we can get the 3D distribution of the mammal. So we can also have something which is like a real-time data of the mammals that gives us, okay, we have some information that we have a group of mammals that are moving from this place to are migrating from one point to another, and we in real time dynamically control our operation condition to cause less harm to them. That could be an interesting thing. We also need some data on the environmental measurements. So we have good resolution of the bathymetry of the ocean, but we would need other things like the temperature profile of the ocean, the salinity profile. The ocean bed also absorbs some of the noise depending on the sediments. we could get some data of the absorption coefficient, which we could maybe incorporate in our noise propagation model. Yeah, I haven't done much literature on the fuel side. I just know that because we deal mostly on the noise side, I'm sure there could be a lot more work to be done on the fuel side of the ship.
Sure, yeah. Optimization problems always have extra layers of challenges if you want to chase them down, I guess. And I guess what's next for you?
Next for me is to complete the 3D framework. So I'll try to graduate around September and then I'll do the internship. Yeah, I'm working with the company IPEX that deals with material modeling. So they have some data sets of polymers that gives us some chemical and physical properties of polymers, and they want a regression model for polymer, in order to estimate the strength and the thermal properties of the polymer. So I would be working on that internship from September. Before that, I'll try to wrap up my thesis and everything.
Well, exciting stuff for sure. Akash, where can listeners follow you online?
I don't have social media where I post a lot of things. They could follow me on ResearchGate where I publish my papers.
Yeah, thank you so much for taking the time to come on the show and share your work.
Thank you very much, Kyle. I appreciate the opportunity.